So I'm interested in talking about forces that are either conservative or non-conservative. This has nothing to do with their political affiliation, but rather it has to do with how they address energy. There are forces that conserve energy and there are forces that do not conserve energy. So forces that conserve energy are, I guess my first definition, definition one, would be a conservative force is conservative forces lose no energy to heat. And maybe I could be more specific about energy. I could call it mechanical energy. Conservative forces lose no mechanical energy to heat. So the energy is either potential or kinetic, and it maintains that state of potential and kinetic. A beautiful definition of a conservative force is you take something and you throw it up into the air, and it, don't drop my carts. Sorry. And it goes upward and it stops and it comes back down. And the way you know it's conservative is the initial velocity upward will be the same as the final velocity when it gets down to that same position. This is from a whole bunch of different kinematic equations. You can prove that this is the case. But if something is going up and it is acted on only by conservative forces, then it will come back down with the exact same speed. That means that over here, the initial kinetic energy is 1/2 mv initial square. I guess I should use knots so that I can be consistent. The initial kinetic energy is 1/2 mv naught square, and the final kinetic energy final is 1/2 mv final square, and the direction doesn't matter because we're squaring those suckers, so we can say that change in kinetic energy is 0 in this case. Now, we don't even have to be this specific. We can still have a conservative force if we do change the kinetic energy. But we have to know, for instance, like let's take this same situation, we have a bowling ball and we throw it upward and it reaches the top. A moment later, it reaches the top. So this energy here, 1/2 mv naught squared, has become what when it gets up to the top? At this height, we could say here, let's say height is equal to 0 because that's our choice. Up here, we're going to say height is equal to h final. So there's no, what I'm saying is v final equals 0. There's no kinetic energy. However, there is some potential energy, and the potential energy is gravitational, and it's equal to m times g times h final. So we've got potential here, and if this potential final is equal to that kinetic initial, then we've got a conservative force. So I guess I can ask you the question, what force is not conservative? And this is a very broad category of force, but I'm going to ask it anyway. Hey guys, what force is not conservative? What force is not conservative?
Force of Barack Obama.
Force of, yes, but what force causes energy to turn into heat? Friction. So that force that is not conservative is the frictional force. Anytime there is friction in a problem, well, there are a whole bunch of consequences of a non-conservative force. Anytime there's friction in a problem, you know the energy will be lost to heat because conservative forces lose no energy to heat. So let's consider what this means. One of the cool things about conservative forces, this could be considered another definition. Conservative forces definition number 2. Conservative forces, well, what can we say? We can say that conservative forces have no change in energy during a closed path. So for instance, one closed path would be starting from here, going to here, going to here, and going to here, and going back. But that's interesting because there's another way to have a closed path that also, let's say this is the initial position and it's also the final position. There would be no change in energy of the system as it moves under the action of only conservative forces. if it takes this closed path. Another way to do this closed path would be to go over here, and then over here, and then like this, and back. So I guess that kind of leads us to definition number 3. And definition number 3 of conservative forces says that the path you choose to take to get from one state to another, path does not affect energy. Interesting. So let's name some conservative forces. We've already seen that, we've already seen that gravity is a conservative force. What else is a conservative force? Some other force that conserves energy. Well, definitely not friction because it's non-conservative. What about electric force? I think the electric force would be considered a conservative force. Can we think of any other forces? The strong force. The strong force and the weak force. Weak being part of the electroweak force. These forces are also conservative. Is there another force? Electroweak, strong, gravity, and weak. All right, we're good. All the forces that you traditionally know about, the standard forces there, are conservative forces. The one weird force that's not conservative is friction. And notice that these are fundamental forces, and friction, well, we haven't really had a good example of why friction occurs. Friction is a macroscopic effect. If you consider some carpet or something, it's very bumpy, and if you try to push a box across it, truly speaking, the box has little bumps all over it. So as the box bumps lock in to the carpet bumps, it will be hard to push the box across the carpet. So it's the very fact that this is large that causes energy to be lost to heat. Heat! Boy, that deserves its own slide. Heat is random motion. So we should just get that up there right now. Since heat is random motion, you can get randomness only in a large system like this. If you have just two particles, and they collide, pew, like that, I suppose we can't really change the heat of this system when these two things collide. So heat is a macroscopic effect. It requires a whole bunch of stuff interacting. The last thing I want to say about conservative forces is we can show where definition 3 would be violated. Recall, please, definition 3, the path does not affect the energy. So what I want to do is I'd like to ask Newton if he could push this weight from this initial position, right here, initial position, to this final position. Newton, would you please push that weight? And he says, sure. So he goes, well, I mean, it's face pushing, so it hardly counts, but he goes kind of directly there, and he says, that wasn't so bad. And you notice the energy of the weight, because it hasn't gone up or down, and it hasn't sped up or slowed down in this exercise, the energy of the weight is exactly the same here as it is here. However, Newton's tired. Newton did some work. So let's bring it back here and ask him to do it another way. Let's ask him to take a much longer circuitous path around to the final location. Newton actually has to turn upside down to do this. He's narrowing in on the destination, and he's there. Did Newton do the same amount of work to get the weight directly there versus spiraling in on the goal? No, the work was very different. Work done by Newton depended on the path. And what is it that was causing the force that opposed the motion of the weight? Why did Newton not, was he required to exert work to get over there? Shh. Can you hear it? Listen quietly. Whoa, there's a magnet in Newton's head. Awesome, watch this. Hear that? Hear that sliding? That's friction, and friction is the reason that the work done by Newton depended on his path, because that force is not conservative.